Okay, let us get started. We're all here. The tests are clearly not graded, but the solution is there on Moodle if you want to look at the solution. And I will try to get them graded as soon as I can, but I do have meetings. Like this afternoon, I have a meeting, so I won't be able to meet with you, Cassie.
Oh, okay.
So that will keep me from grading this afternoon. Tomorrow I have meetings as well, so I won't get much grading done tomorrow. But I'll try to get them done at least over the weekend if I can. Back to relativity. We're going to look at addition of velocities. Now I'm going to start with a few clicker questions, and then we'll get into addition of velocity. So first, supposing that Usain Bolt carries his own stopwatch, and assuming his stopwatch and the stopwatch of the official are exactly correct. And for Michaela, we're going to assume that that stopwatch doesn't even move with the beating of his heart. It stays perfectly stationary with his body. Who has the shortest time for him to run the 400 meters? I went big with him. Would it be that they're the same, that Usain's is shorter, that Usain's is longer, or it depends on if it's a straight track or an oval track? That's why I chose 400 meters, because you do a lap for the 400 meters as opposed to half a lap for 200, straight away for 100. It's not working at all.
It's like loading. It's trying to find. Oh.
Is it starting to work?
Yes.
Excellent.
Never mind.
Never. Okay, he's in. He's in. Unfortunately, my grid didn't show me the answers here. So I can't see what your answers are. So I just have to go with what the answer was. I hope the rest of them aren't like this. I made this one at home using a different version of Turning Point, so it could be all like this. Okay, so with this, what's the key concept we have to use to decide who measures the shortest time? Well, yes, it is special relativity. Okay, we're dealing with time dilation. Proper time. We need to determine which reference frame is going to measure the proper time. Now, that does not mean which reference frame measures the correct time. The proper time is the time that is the shortest that can be measured in any reference frame. And what was our way of determining which reference frame is going to measure the proper time?
One that has a stopwatch at the beginning and
And the stopwatch is the beginning and end,
The thing doesn't move relative to the clock.
and it doesn't move. And of course, it has to, well, our time dilation calculation, because if he does a complete lap, then both stopwatches could be stationary for the entire time in their reference frame, and each stopwatch in its reference frame didn't move. But when we deal with special relativity, going to what Jaron said, the special relativity calculations only work in an inertial reference frame. And so when you put all of these together, you get the convoluted answer that Usain's reference frame is the reference frame that measures the proper time. But there's a trade-off. Usain measures the proper time, which is the shortest time possible. What about the length of the run? Usain's going to measure that the run was actually contracted a little bit. So he actually didn't run 400 meters. So, if he's going close to speed of light, so this makes a difference, he's like, man, they timed me too long, but it was a short track anyway, so it probably works out. Because, in fact, in the end, it does. And, of course, what really matters is who wins the race. Okay. Now looking, first a clicker question. Guess what's on the next slide? A problem with cosmic rays. an example, a practical example where plenty of measurements have been made. Cosmic rays, energetic particles, they're like photons, or like protons, excuse me, I misread that enter the Earth's upper atmosphere from space. They collide with atoms, and they will produce these particles called muons. And those muons have a short lifetime. Half of them will be gone in 1.5 microseconds. You wait another 1.5 microseconds, half of the remaining ones are gone. So you'd have 1/4 and so on. So you have cosmic particles coming into the Earth's atmosphere, and then they create muons that are coming toward us. And the muons are coming really fast. 0.995 times the speed of light. So the muons are flying toward the Earth really fast. They only have a lifetime of 1.5 microseconds. Before I go further with the question, we're going to have the clicker question that just asks about length, the distance. So clicker question. In the Earth reference frame, the altitude where the muons are created is 4,500 meters above sea level. What is the altitude above sea level in the muons reference frame for the same position? You're right, it's not. I am really doubting my using the new version at home. There, now it is. Unfortunately, the old version is no longer available in case people care. Okay, everyone but Toussaint. There we go. All right, and yeah, it's just not going to show me answers today. I'm sorry about that. I won't do clicker questions at home. I'll wait to do those at school. So, what is it? What's your strongly held belief? Okay? Everybody that made an effort to let me know said less than 4,500 meters. What was our key concept here? Okay, so this was a length contraction issue. And so the proper length is the length that is the longest possible. And length contraction is going to be shorter. And what reference frame measures the proper length?
Outside.
Proper length.
Yes. Well, it is the Earth in this case, but why? What's our rule for determining which reference frame is going to measure the proper length?
That's what you said last time.
Yes, that's what I said last time. That's not exactly the rule. Yeah, the start and end points don't move. So the muon sees the Earth coming toward it. That end point is moving. Whereas the Earth frame, the top of the mountain is stationary. Bottom is stationary. So the muon sees the mountain moving, so the height of the mountain is not going to be the proper length in the muon's frame. But the Earth frame, the mountain is stationary, so that's the proper length. So the muon sees a contracted length. Now, I think the next slide is just going to say, what is that contracted length? Yes, what is that contracted length? Okay, that has the answer on it. I don't want to see the answer. I want to do the work. So actually, I'm going to go back to this slide, which has the pic. Oh, that doesn't have the picture. Well, poo. I'm going to go to the clicker slide and do the work here. So I have a mountain that, measured by Earth, has a height of 4,500 meters. And we have these muons that are traveling downward with a speed equal to 0.995 c. What's my equation for length contraction? Because we identified this as a length contraction issue.
L is L sub naught divided by, I think it's gamma.
Okay. L is L sub 0 divided by gamma, where gamma is that Lorentz constant It's not actually a constant. 1 minus v squared over c squared. So not a constant. I swear we call it a constant, but I could be wrong. So we just have to do that calculation for gamma first. When you're doing relativity problems, I always just calculate gamma first because I figure it's going to come up somewhere. Let's have that number. Notice the c's cancel. It's just 1 minus 0.995 squared. Do you have that for me, Tori?
Gamma should be 10.01.
Okay, so gamma is 10.01. Now I can put that into my length contraction equation. The length is equal to the proper length divided by gamma, which to 3 significant digits, because that's all we really have, is 450 meters. I can divide. Just have problems some days. So the mountain is 1/10 as tall as measured by the muon and coming toward it. So now the question that follows this up is, do a significant fractions of the muon survive to hit the Earth? If we measure this in the Earth frame, we had (1.5), that I believe that was microseconds, right? Was the lifetime. And so if we did it in the Earth frame, and we said, okay, should it have a half-life of 1.5 microseconds, the time that it takes time to fall is going to be equal to the distance divided by the speed. Right? That's very simple. So that would be 4,500 meters divided by 0.995 times, between friends, I'm just going to put 3.00 times 10 to the 8th meters per second. And what do we get for the time that it's going to take for them to fall from that altitude to hit the Earth?
1.5 times 10 to the minus 5 seconds.
So that means half of them should come and hit the Earth, assuming we did our calculation here correctly. But what about in the muon's view? So this is the Earth view. Oops, this second calculation was the Earth view.
Half of them?
Yes, because this is equal. Oh, wait. 1.5 times 10 to the minus 5 seconds, micro. Yeah, that's right. Actually, yeah, you're right. That's 15 microseconds. So it's actually 10, so 1/2 raised to 10th power. Yes, I was wrong. Thank you for correcting me. So that's equal to 10 of the time 1/2. Therefore, the number that hit should be the number we started with times 1/2 raised to the 10th power. And what's 1/2 raised to the 10th power? It's basically 1,000, right? 1,028, isn't it? Somebody? Anybody? Computer person? 1,024? Okay. So it's basically going to be 1/1000th of what you started with. Okay, so there, thank you for correcting me. Now if we look in the muon's frame, the time to fall is, once again, distance over speed, but that's 450 meters divided by 0.995 times. I don't need a calculator to do this since we did the other one. That's the one that's 1.5 times 10 to the minus 6 seconds, or 1.5 microseconds, which means that n is equal to n0 times 1/2 raised to the 1, because it's just 1 half-life. So half of them strike the Earth. Now, very practical question. Is it going to be both of those are true? No, it's not going to be both of those are true. So we can do a measurement and see how many particles hit the Earth. The Earth calculation is denying relativity. The Earth calculation is saying if there's no relativity, the half-life I measure for the muon in the lab is this, and so that's how long it has to fall. Says you have virtually none. So scientists do this measurement. They measure and they find that this is the answer. So a practical measurement that backs up relativity, that we do have the length contraction. We could have also used time dilation to make the calculation. Either way would have given you the same answer. So why do I do this one? To give you a practical example of things that experimentally can be done to verify the predictions of special relativity. Because if you don't have experiments, all you have is an empty theory, which is not very fulfilling, not something most people are willing to accept in science.
So which one was it? It was the half?
The correct answer is half. Because as measured in our reference frame, the half-life is dilated to being 10 times longer, or as measured in the muon's reference frame, the distance it has to travel is contracted to 1/10 as far. Both give you the same answer of 1/2 gets here. Okay, now addition of velocities. That was the topic du jour. We already talked about things like I gave you the example, first day of relativity, of a child walking on a school bus. And what I gave you for how to add the velocities was the velocity of the child with respect to Earth was equal to the velocity of the child with respect to the school bus, plus the velocity of the school bus with respect to the Earth. So if you look at this, I had the same indices for the inner two, and then the outer ones were the ones I wanted for my answer. But we run into problems using this with relativistic situations. For instance, if B here is driving her little spacecraft and shoots out a probe, and if she's traveling at VBA, the speed of B with respect to Abe is, let's say, 1/2 the speed of light, and she shoots out that probe with respect to, now I'm going to change this, I'm going to put V of the probe with respect to B is equal to 3/4 the speed of light. So she's shooting that probe out with 3/4 speed of light as measured by her. And Abe says she's traveling at 1/2 the speed of light. Then what speed is Abe going to say the probe is traveling? If you use the equation here in blue, Abe's going to say, well, that's simple. That's going to be, Abe wants the velocity of the probe with respect to Abe. So he's going to put velocity of probe with respect to something, plus the velocity of that something with respect to Abe. And what's the intermediate going to be? B, right. Get that? Going to be B. But if he puts in those numbers, he gets 3/4 C plus 1/2 C is equal to, oh, woe is me, that's going to be 5/4 C. Abe can't say the probe is going faster than the speed of light. That was our second assumption of relativity, is the speed of light, or postulate, second postulate of relativity. The speed of light in vacuum is the same in all reference frames, and nothing can exceed it. So that probe can't be going 5/4 the speed of light in Abe's reference frame. So this cannot be correct. Now in class on Tuesday at 11:30, we will work through the derivation for the equation for relativistic addition of velocities. But the equation for those who don't have calculus, I can't do the derivation for you, I'm sorry. So I just have to give you the equation. The equation is that I have the same thing in the numerator, but I have to divide by something. And that thing I divide by is 1 plus the product of the two velocities on top divided by c squared. So for the actual speed, according to relativity, well, I have it written right there. I don't need to rewrite it. Let's just put in the numbers. That's going to be 3/4 c plus 1/2 c divided by 1 plus 3/4 c times 1/2 c divided by c squared. So the top gives me 5/4 c, and the bottom is 1 plus 3/8. Okay, 1 plus 3/8, that's going to be 11/8. Using our invert and multiply rule, okay. For those following along at home, 8 divided by 4 is 2. 2 times 5 is 10. 10 divided by 11, 10/11ths. And so this relativistic, what was that?
You said no following along at home was an option.
Sorry, those of you following along in the classroom that is approximately 80 degrees, I'm sweating like I don't know, what sweats a lot? A horse run hard. The relativistic equation for addition of velocity has the advantage of giving us at least an answer that we accept as possible. Now, just doing the calculation doesn't say it has to be correct. The derivation should help to give more confidence, but like I said, without calculus we can't do the derivation. But here is an example that helps to give you a little more confidence in the equation. What if B had fired a a photon cannon? By definition, a photon cannon is particles of light which travel at speed of light. So if she had fired a photon cannon, then we would have had this one here was just c. So speed of the photon cannon would be c. On the bottom, I also put the c there. And then just a little rearrangement, factor out the c on top. So c is 1, and v becomes v over c since I factor out c. Cancel the c's on bottom, and I have, those are exactly the same thing. Those cancel, and the speed of the photon torpedo is going to be the speed of light as measured in any reference frame. Doesn't matter how fast B is going with respect to Abe, the light is still going to be traveling at the speed of light. That is exactly what was said by our second postulate of relativity. So that's something that helps me have a little more faith in the equation for addition of velocities. Now, one thing I have to say about this addition of velocity equation. This is the equation for addition of parallel velocities. There is a different equation for the addition of perpendicular velocities. I mentioned to you that there was a question in the concept coach that was incorrect, that asked about the Doppler shift. And I have a slide on the Doppler shift coming up, so that's where I'll talk about that. But it has to do with, you still have a dilation, a time dilation, when you have transverse velocity, and that still causes you to have a different equation. You can't just add them as vectors when you have perpendicular velocities. But in this class, we won't deal, as in the Monday, Wednesday, Friday, we won't deal with the addition of perpendicular velocities, only parallel velocities. So how do we do problems that come up with addition of velocity? Well, first, you need to make sure that you have identified your reference frames carefully and identify each velocity as the velocity of this object with respect to that object. Second, recognize that if you switch the indices, it requires you to change the sign. So if I measure the speed of Chad with respect to me, It's the same magnitude as the speed of me with respect to Chad. But if Chad sees me coming this direction, I'm going to see Chad is going that direction. So that's where the minus sign is at opposite directions. Make sure that you have things that are in a straight line for Monday, Wednesday, Friday for Physics 111. And then you put them into this simple equation. And the rule is, oops, that was the wrong place. These two things have to be the same indices as these two, in the same order. And then the interior indices are the same. As long as you have your equation like that, you're good to go. So you may have a completely, all of the indices reversed. Well, you just reverse them, change the sign, put them in, and you're good to go. So you can have a negative value. You put in the negative value if it's negative. And make sure you put in the negative on top and on bottom. And so that's how you deal with these. They're actually pretty simple mathematically, but once again, kind of bizarre philosophically to think that when I add the speeds of two things together, the total is not the sum of the first two. That seems bizarre. And that's where relativity is, truthfully, bizarre. Okay, a clicker question to make sure we were following along. Okay, once again, I can't see the answers. Hopefully everyone was following along. I don't like not seeing the answers. I never know who answered what, but I can see if people understood or not. Right? That's the big point of using these, to make sure that people have thought it through and put an answer out there, and then we can check it right away and see, did they understand or do we need more? The answer should have been B. Light always travels at the speed of light in any reference frame. So we don't have to put it in the equation. I did the equation. We saw the equation is always going to give us C if the object's moving the speed of light, C. So that was just a check.
Question.
Yeah, go ahead, Tristan.
So, it doesn't matter like what the math says. It's always has to always C.
The math had better agree. If the math doesn't agree, then we have a problem with our theory. Right, but I didn't have to do the math because I know it's always going to be C for the speed of, for the speed of light. So in this case, I just didn't go to the math because I knew the answer. But if I did the math, it had better given me C.
Can you do the math?
Well, we did before, but it was... actually, let me go back to that slide so I can see the right numbers. So we have V of the torpedo with respect to Earth is equals V of the torpedo with respect to the spaceship plus speed of the spaceship with respect to Earth divided by 1 plus V torpedo spaceship V spaceship Earth divided by C squared. So there's my equation. Now I put in my numbers, so that's going to be C plus 0.50C divided by 1 plus C times 0.50C over C squared. If you add the top together, the top gives you 1.5C, and the bottom gives you 1.5, and so that's equal to C. Right? The math has to agree. If it doesn't, then our equation is wrong. Okay, so here, just another practical example. two spaceships travel at high speed in the same direction. So I have, there's one spaceship. Here's my other spaceship. And I have the speeds, and I have somebody, an observer aboard ship 1, oh, excuse me, I have to read up here. An observer on a nearby planet says that speed 1 is behind and moves speed of 0.90 c. So I'm going to have, chose the wrong color, sorry. V1, or V1 with respect to the planet is equal to 0.90 c. And speed 2 with respect to the planet is equal to 0.70 c. And then the question is, according to observer on board ship 1, how fast is ship 2 traveling? Now, here's a first thing to determine. What subscript do I have for the thing I'm looking for? V subscript what? That's right. The first subscript is the thing you're looking at its speed. The second subscript is the reference frame you're making that measurement in. So if I'm looking for V21, then I'm going to have V2 something plus V something 1 over 1 plus V2 something, V something 1 over C squared. What do I put in for that underscore? P. So everywhere I put an underscore, I come back and I replace it with a P for the planet. Now I have V1 planet, but I don't have V2 planet, or excuse me, I have V2 planet, I don't have V planet 1. So how do I find V planet 1? V planet 1 equals minus V1 planet. So that's going to be minus 0.90 c. And now I can put my numbers in. So that's going to be equal to V2 planet 0.70 c plus V planet 1, which is minus 0.90 c. The top is easy. 0.7 minus 0.9 is minus 0.20 c. The bottom, 7 times 9 is 63. 1 minus 0.63 is 0.37. And so we have minus 0.20 c divided by 0.37 c. What did you get?
Negative 0.541-ish.
Okay, so the 2 sig figs, minus 0.54 c. I'm guessing nobody would have gotten that answer just by out of the blue looking at the numbers. You have to go through the process, hence the doing an example problem. Any questions about how to do this addition of velocity thing? You saw how I set up the equation? And then I determined what I needed, used the information given to flip things, and I was good to go. Okay, oh, yes. I had this nice picture for a solution. Well, too late now. Now for the Doppler shift. In section 17.4 of the textbook, we talked about the Doppler shift if something is moving toward or away from the source. And you could have a moving source and a moving observer, and combining the moving source and the moving observer, you got this equation for the Doppler shift. The frequency observed by an observer is equal to the frequency of the source multiplied by that ratio, the speed of sound plus the speed of the observer divided by the speed of sound plus the speed of the source, where all directions are positive is the same direction for everything. As long as you have the same direction for everything, that works out. So that's the Doppler shift that we saw before. And that gave us basic things like if an object is coming toward you, you're going to have the frequency shifted to a higher frequency. If an object is moving away from you, it's shifted to a lower frequency. Now we look at light waves and the Doppler shift for a light wave. Now light waves have something significantly different from sound waves. The sound wave speed varies with how fast the medium is moving. If you have a wind, that'll change the speed. And so that makes sound a little different. And with time dilation, we have to take time dilation into effect when we calculate the Doppler shifts for light. And so once again, without doing the derivation, it's not done in the textbook, at least I didn't see it. This here, the lower equation, is the equation for the Doppler shift for relativistic, using relativity. Whenever you do light, this is the equation you use for the Doppler shift. Now you'll notice right away it has a significant difference in that you have a square root that wasn't there for the normal classical Doppler shift for sound. You have that square root, you have the speed of light in vacuum, constant, plus the speed of the object divided by speed of light in vacuum minus speed of the object. What does this do? What is this net result? It's still the same thing. If something's moving toward you, then you're going to have a shift to higher frequencies. If it's moving away from you, you have a shift to lower frequencies. But the shift is by a different equation. And this is only if you have parallel motion. If you have transverse motion, if you have something that's going around you in a circle, if it was sound, there'd be no Doppler shift whatsoever. You would hear the frequency of the source because the distance from the source to you is remaining constant. But with relativity, with an electromagnetic wave, if you have a source that's going around you in a circle, even though the distance between you and the source is staying the same, the time is passing at a different rate for the source than it is for you. And so that's going to result in a Doppler shift. And hence, the correct answer to the question that was in the concepts coach, which I sent a message so everybody should have known, is that you actually have a red shift for the case of an object that is at a transverse velocity. Now, that equation, or that problem, I have to go in and manually fix because it had just the same, that one I have to fix, and the other one that had the same answer for all three. I have to manually fix those because, one of them with the same answer 3 times, all of them being wrong, that's a problem. And I just have to go through and give people credit because what are you going to do? There's 3 answers that are identical. You may have guessed the one that they wanted to mark right or not. No way of knowing. So I will spend some time and go through and do those manually just to make sure you're confident that I'm paying attention and not just saying, whatever, it'll all balance out in the end. Momentum. The equation or the problem I was just talking about said, if an object's speed doubles, what happens to its relativistic momentum? Well, we cannot, for relativity, if things are going at a relativistic speed, we can't use momentum as mass times velocity. That's no longer true. And so the correct equation for momentum is mass times u. Why u? The textbook says, note that we're now using u because we don't have 2 observers. We only have 1 observer and an object. And so u is the speed of the object with respect to the 1 observer. So u is still speed. It's just they used a different symbol, and I want to try to be consistent. Now, if I was really going to be consistent, the textbook used u here instead of v object. I put v object, that's what u means, the speed of the object. So momentum has a different equation. And right away, you might say, well, shoot, why did we learn momentum as mass times velocity when now we learn it's something different? We could have used this equation all along. If the speed is, let's say, 20 meters per second, what is gamma approximately? 1. In which case, mv was perfectly correct. It's only when you get up to high speeds where gamma is measurably different from 1, you had a homework problem that had you calculate what speed is necessary for gamma to be 1.01. That is a 1% error. What was the speed for a 1% error? I don't remember. I'm hoping somebody here does. Nobody remembers? The speed, the homework problem that had you calculate the speed to have a 1% change in gamma, that is gamma is 1.01 instead of 1. It's what? 0.3c maybe? Yeah. So it's a pretty fast speed before relativity makes that equation we learned long ago incorrect. But if you're using relativistic speeds, if you double the speed, what happens to gamma? Not smaller, it gets bigger because you're subtracting a bigger number in the denominator. So gamma gets bigger. So what happens to the momentum if you double the speed? It increases by more than double. So that would have been the correct answer there if they had had it as an option. Now notice gamma here is written in terms of u as well. So you don't get confused and say, wait, I have u, but where's v? Where I have v, but where's u? The u means the speed of the particle, and so gamma is the gamma for that particle using u. Now, in and of itself, that's pretty simple. But here is something that may be a little more troubling to you. We learned, like in week 2 or week 3 of the first semester, that Newton's second law was net force is mass times acceleration. And that equation is incorrect. That's an approximate equation for a special set of circumstances. Later on, we learned about momentum, and we learned to rewrite Newton's second law as the net force is equal to the change in momentum over change in time. That is a correct equation. That's really Newton's second law. So this here, notice it's got the unequal sign. Net force is not equal to mass times acceleration. The net force is equal to the change in momentum divided by change in time. Well, momentum has gamma mv, or gamma mu. And so you have two things that have velocity in there. If gamma is staying approximately 1 for everything, then our approximation worked out. But if it's not, well, that's not going to work. So Newton's second law, this is the correct form. And I believe when we got to that form, I emphasized this is the correct form of Newton's second law. The other one was an approximation. And so here is where we can have some, if you do the calculations, you have some real differences. Now let's do another problem. How am I doing on time? Yeah, good. I got 8 minutes left. Do another problem. I have a proton. So here's the little red proton that's moving at 0.70 c and has a head-on collision with a stationary nitrogen atom. And it bounces back with a speed of 0.63 c. What is the speed of the nitrogen atom after the collision? Well, I have my system of the proton and the nitrogen atom. Net external force on this, we're not told of any crazy things acting on it, so we assume the net external force is 0. If the net external force is 0, then Newton's second law tells us, the correct form of Newton's second law, sum of the forces is equal to change in momentum divided by change in time. If the sum of the forces is 0, what does that tell you? The momentum is going to be conserved. There's going to be no change in momentum. So all I have to do here is say, well, the momentum of the proton initial, it's all one-dimensional, so I'm dropping the vector signs, plus momentum of the nitrogen initial is equal to momentum of the proton final plus momentum of the nitrogen final. Conservation momentum. Momentum of the nitrogen initial, that was easy, that was 0. What's the momentum of the proton initially? So that's going to be gamma proton initial, mass of proton, times, I'm going to put speed of the proton initial. I don't like to use u. Well, now that looks more complicated. And it is more complicated. Because now I need to calculate what that gamma is. And I need to know the mass of the proton. Well, what we were given is that the mass of the proton is 1/14 the mass of the nitrogen. So we'll just use 1, as in 1 atomic mass unit, for the mass of the proton, 14 for the mass of the nitrogen. So mass of the proton is equal to 1U, mass of the nitrogen is equal to 14U. I need to calculate gamma for the proton initial. That's going to be 1 divided by square root of 1 minus 0.70 squared.
1.40.
And so the momentum of the proton initially is going to be 1.40 times 1 atomic mass unit times 0.70 C. So there's the momentum of the proton initial. What about the momentum of the proton final? I need gamma for the proton final. It's going to be a different gamma. Mass of the proton, V proton final. So that was a 0.63 for its speed. Calculate the gamma there.
1.29.
Why do I have the minus for the minus 0.63 C? Because it rebounded, it went the other direction. And so, my handy calculator person?
Negative 0.8127.
I forgot the U up above. U times C for the units. Okay, so I've got the momentum of the proton initial and final. I know the momentum of the nitrogen initial was 0. And so the momentum of the nitrogen final is equal to momentum of the proton initial minus momentum of the proton final. And of course, plus 0, the momentum of the nitrogen initial. So that's going to be okay, 987. So 1.793 Cu. C is the speed of light. U is the atomic mass unit. Well, we weren't asked to find the final momentum of the nitrogen. We were asked to find the final speed. So that's equal to gamma nitrogen final mass nitrogen V nitrogen final. So that's well, at this point you can see we're going to get there. I only have 2 minutes. I don't want to finish the calculation because of the time. I could divide both sides by 14 and cancel out the u's. And then I have on the left side something that has V nitrogen final 2 different places. So it takes a little manipulation, but you can solve it. So that's how you do the conservation of momentum problem. A little more advanced. Now it turns out that there are some matrix methods that we can use to make it simpler. Now I have to hit the high points. I'm going to skip this question, especially because I can't see your answers anyway. The untrue statement was that relativistic momentum is mv. So I'm skipping that question. Energy. You've all heard E equals mc squared. Not exactly right. It should have E0 is equal to mc squared. Einstein theorized that mass is just a form of energy. And so everything that has mass contains energy that he called the rest energy. And the rest energy is the mass of the object multiplied by the speed of light squared. So this rest energy is not the same as chemical energy. Chemical energy is a different type of energy. Just because something has mass, it has energy. The more mass, the more energy. And this equation allows you to calculate the energy mass contains. Where is this useful? Atomic bombs, atomic energy. What's going on there is the conversion of mass into useful energy. That's what we're doing when we're making those. Now I say useful, destroying things is not necessarily useful. Just quick notes, we often use electron volts. We've discussed them before. 1 electron volt is 1 electron charge times a volt, 1 volt. So it's 1.602. We often use those for energy, or we will use things like mass in electron volts per c squared. Or for the electron, the mass is 511 kiloelectron volts per c squared. For protons and neutrons, we put them in mega electron volts per c squared. Why do we use these crazy units? Because it makes it so the c's will just multiply out in our calculations and we don't have to worry about the number. Just a couple more things, clearly not the question or the example problem. We will work that stuff out later anyway. 2 invariants we've learned about. Speed of light is the same in all reference frames. Mass is also the same in all reference frames. Doesn't matter what your reference frame is, you'll have the same mass. Now you can have different weight, right? That depends on G. Final things are going to be kinetic energy and total energy. So come on, fast. So this here, I work out what the kinetic energy is. I had to use calculus to calculate the kinetic energy. That last integral is not as simple as it may look to you. But by taking work is equal to the integral of force dot distance, we find that the kinetic energy relativistically is parentheses gamma minus 1 and parentheses mc squared, which is nothing like what you're used to seeing. It does have v in it, though, because gamma depends on the speed. And at low speeds, gamma minus 1 turns out to be 1/2 v squared over c squared. So that your equation is 1/2 mv squared at low speeds. Okay, so the last thing that I need to show you is that Einstein said, you know, that kinetic energy is, well, kinetic energy plus the rest energy should equal your total energy. And so he theorized that your total energy is gamma mc squared, and your rest energy is mc squared, and so kinetic is just the difference in those two. So this here is how we understand energy from a relativistic standpoint. Okay, I'm 2 minutes over. Have a swell hump day.